So I guess it is time to begin. Attention, s'il vous plaît. Okay. So I'm very happy to give another talk, and I'm very happy to tell you that this is my last talk, because by noontime today I'll be able to enjoy the rest of the workshop. So I was unsure exactly what title to give this. In fact, the title that you see on the program was the working title. Benoit asked me what I wanted to talk about. I said, well, I could talk about how you form quantum states of light and this and this and this. And somehow that got into the program as the official title. So I have a real title and a subtitle. I think the real title and the real message is Nonlinear Optics, the Enabling Technology for Quantum Information Science. Doesn't that have a nice ring to it? That all these people doing quantum information, at least most of them, couldn't be doing it if it were not for us. But then the subtitle of the talk is Generating, Characterizing, and Utilizing Quantum States of Light. And I had noted in the first talk that my primary affiliation is with Ottawa, that my traditional affiliation has been with Rochester, but that I am now a visiting professor at the University of Glasgow. And I take these things very, very seriously. In fact, it was Miles Paget who arranged for me to be a visiting professor at Glasgow. So the very first thing I did after receiving this appointment was to realize that if I'm going to be at a Scottish university, I have to look and act like a Scotsman. So I went out and bought myself a kilt outfit. I assure you this is the Boyd plaid. So why would I wear someone else's kilt if I can wear my own? So of course I'm always looking for excuses to dress up like this. It wasn't quite clear that Les Ouches is the sort of place where you come dressed like this, but maybe it was a mistake that I didn't. Okay, so let's get right into the talk then. This is the brief outline of what I'll be doing over the next hour and a half. I say hour and a half. I'm going to work very, very hard at not using up the entire 2 hours. So first is generating and characterizing quantum states of light, then quantum information based on the orbital angular momentum of light. Then I'll talk about quantum imaging, and then if there's time, just some related work that I think you might find interesting. So let's go into the generating and characterizing quantum states of light. This was actually this is a slide that I just flashed by you in my first talk on Tuesday. So parametric down conversion is a source of entangled photons. So parametric down conversion, well, at one level it's just difference frequency generation, but it's difference frequency generation without any input fields. So this process grows from quantum noise. And I'll use slightly different notation now. We'll call this the pump photon, we'll call this the signal photon, we'll call this the idler photon. And this would be a typical phase matching diagram for the parametric down conversion process. Now, we say that the signal photons and the idler photons are entangled, but to make that thought precise, you really need to tell what degrees of freedom you're talking about. And in fact, these photons, signal and idler photon, are, in the most general case, simultaneously simultaneously entangled in their polarization, in time and energy, in position and transverse momentum. And just leading into the second topic, where I'm going to talk about the implications of nonlinear optics for orbital angular momentum states of light, implications for quantum information. They are also entangled in angular position and orbital angular momentum. And why do we care about entanglement? Well, fundamental tests of quantum mechanics. Of course, Einstein, as we know, didn't like the fact that things were entangled. That entanglement is a true feature of nature. So in the 70s, 80s, and 90s, people were actually doing very careful tests and found out, yeah, entanglement is for real. John Clauser did it first, and and then Alain Aspect, and later Anton Zeilinger. Well, those are the three that I will mention because they won this big award for doing it. So the Israelis have decided that these are the three key people. And for quantum technologies. And as the talk goes on this morning, I'll try to indicate how the ability to produce entangled photons has very important implications for quantum technologies. Let's take a careful look at what I mean when I say that these photons are entangled. And I think time-energy entanglement is the one that is perhaps the most dramatic conceptually. So let's talk a little bit about that one. So first of all, when we say that they're entangled in energy, all we mean is that if I measure the energy of this photon, I can immediately deduce the energy of this photon. Say, well, I didn't need you to tell me that. You knew that already. But it gets better. If instead of measuring the energy of this photon, I measure the exact moment of time at which this photon leaves the nonlinear crystal, we find that it's exactly the same moment of time at which this photon leaves the crystal. Now, so you can measure the time of this one and you deduce the time of this one. You can measure the energy of this photon. You can deduce the energy of this one. But if you measure the time at which this photon is emitted, you lose complete knowledge of the energy of this photon. And if you measure the energy of this photon, you lose complete knowledge of the time at which this photon was emitted. Incredibly, you can wait until the signal and idler photon are out of the crystal, long after they've left the interaction region, and only then decide whether you're going to measure the time of emission of this photon or the energy of this photon. And you can decide after the fact which one to do, and you always find this complete correlation with the corresponding property of the other photon. So that is why entanglement is so counterintuitive that Einstein couldn't even bring himself to accept it. And it's why it's so important, because there are quantum technologies that are based on this property of entanglement. So let me just give you a simple example. This was an experiment that my colleagues at Rochester and I did over 10 years ago. We did a measurement to demonstrate the EPR paradox. So let me remind you about the EPR paradox. So Einstein, Podolsky, and Rosen said, let's imagine that you have some interaction region here, and you have two particles that are emitted. And since the system was originally at rest, these two particles leave at the same place. And since momentum is conserved, if this particle is going to the left, this particle is going to be going to the left with exactly equal and opposite momenta. So now why is this paradoxical? Well, because they say, well, if I measure the position of this photon, I will know with complete certainty the position of the other photon, because they're entangled. But on the other hand, I could measure the momentum of this photon, and then I will immediately know the momentum of the other photon. Now, we know, do we know? We know that the measurement on particle 1 cannot influence particle 2, and in a certain sense that means that there's the uncertainty in the position of x2 vanishes, and simultaneously the uncertainty in the momentum of particle 2 vanishes, and that this is in conflict with the Heisenberg uncertainty relation. So this is the paradox that Einstein, Podolsky, and Rosen put forth. So we did the experiment. And of course, we're not the first person to do the experiment, but I felt that ours was an unusually clean version of the experiment. I mean, Jeff Kimball did it long before we did, using the quadrature squeezing components of a light field. If Einstein were alive, would he recognize that you did his paradox? So we actually did this experiment measuring the position and the transverse momenta of photons. Okay, so we have a diode laser, doubling crystal, BBO crystal, creates two entangled photons, type 2 polarizing beam splitter, one photon always goes down this arm, other photon always goes down this arm. We keep this slit fixed, we scan this slit, so we find the probability distribution for the position of photon 2 conditioned on the fact that we knew that photon 1 was measured in exactly this place. Then we added a lens to the setup. And the lens just allows us to work in the far field. And the far field then is the transverse momentum space. So we repeat the measurement and we get the conditional probability distribution for the momentum of photon 2 conditioned on knowing the momentum of photon 1. You measure the width of this distribution, the width of this distribution, and you find that this uncertainty product is 0.1 h-bar instead of much smaller than a half h-bar. So this violates Margaret Reid's version of the EPR inequality. 2 independent quantum particles could not have an uncertainty product that's this small. So indeed, the prediction of Einstein, Podolsky, and Rosen, which they found to be so counterintuitive, is exactly what you do measure when you go to the laboratory and do it. Okay, so this is just an example of the sorts of fundamental tests of quantum mechanics that you can perform using entangled photons. Now, what are the other tricks that you can do with nonlinear optics that are of importance to quantum information science? Well, the other is that nonlinear optics can produce squeezed light, and squeezed light can be important for sub-shot noise limited measurements. First, let me just tell you, or perhaps remind you, what squeezed light is. So let's consider a coherent state of light. Well, classically, a light field has a precise electric field vector. You can plot this in the complex plane. Here's the real part of the field. Here's the imaginary part of the field. Classically, there's a well-defined point here. But because of quantum uncertainty, you don't really know precisely what the electric field vector is. You could say that vacuum fluctuations add on to the classical field and create some uncertainty. So a coherent state has some uncertainty in the exact value of the field amplitude. Now, what we mean by a squeezed state is that perhaps the uncertainty is larger in one direction than it is in the other direction. I see now that this is not a very good picture I drew, because the area here is supposed to be exactly the same as the area here, but just picked up on that now. But the point is that you have a lot of uncertainty in this quadrature, but very little uncertainty in this quadrature here. So if you make a measurement by direct detection, this doesn't help at all. But if you do a measurement using homodyne detection or coherent detection, in homodyne detection, you can choose which quadrature of the field you want to look at. So you can just choose to make the measurement here, and then you've performed a measurement with higher accuracy than what would be considered the standard quantum limit, or better accuracy than the shot noise limit. So this is very important for precision measurements, for quantum enhanced metrology. People are now implementing these ideas at LIGO, gravity wave detectors, because gravity waves are very weak. So you have to make very, very exacting measurements of the displacement of the mirrors when a gravity wave would sweep by. So how do you form squeezed light? Well, you take coherent light at frequency 2 omega, and you pass it through a second order nonlinear crystal, and as if by magic, the light comes out squeezed. And why does it come out squeezed? Well, you look at this phase matching, you look at this energy level diagram, and you see that the generated light will have some specific phase relationship between the signal photon and the idler photon. And because there is a fixed phase relationship between the two, that's what gives the output a tendency to have different amounts of noise in one quadrature than in the other quadrature. Of course, me saying those words doesn't make it true. You have to work your way through very complex calculations in quantum electrodynamics to convince yourself that this is true. But I think the intuition is at least as important as going through heavy-duty math. Okay, important comment. We said that there are two main resources for quantum information that nonlinear optics can provide. One is squeezed light, the other is entangled light. But they are really, in a very real sense, they are two sides of the same coin. Because if you take two entangled beams of light and you mix them on a beam splitter, you will get out two beams of light that are squeezed. So you don't have to do one or the other. Once you have a quantum state of light, you can use classical techniques to manipulate the exact form of that quantum state of light. Okay, so, now let me tell you about another quantum feature of light. It's called the Hong-Ou-Mandel effect. I taught nonlinear optics to Hong and O. They were both students of Len Mandel at Rochester. So, yes, so I will take credit I will take credit that the world owes the Hong-Ou-Mandel effect to me. Okay, so what is the Hong-Ou-Mandel effect? Okay, here's your pump photon, here's the parametric down converter. You generate two entangled photons. But the fact that they are entangled is not the key issue here. The fact is that if you do this correctly, these two photons are indistinguishable. Now, when two indistinguishable photons meet at a beam splitter by a strange but wonderful quantum interference effect, which is actually not that hard to convince yourself. When two identical photons meet at a beam splitter, half the time both photons leave through the upper port, half the time both photons leave through the lower port, but you never get one photon here and one photon here. So that's called the Hong-Ou-Mandel effect. How do you study it in the laboratory? Well, this beam splitter here, let's say that you have the ability to translate the beam splitter up and down. And you measure the coincidences between the click on this detector with that on this detector as you slowly translate this up and down. And you get a curve that looks like this. So when the beam splitter is at the symmetric position, you never get a coincidence count, because half the time both photons leave here, half the time both photons leave here, you never get one photon here and one photon there. But if you translate the beam splitter away from its symmetry position, then the photons become distinguishable. You say, well, there's a photon that arrived earlier and there's a photon that arrived later. So they are no longer distinguishable, and you start getting coincidence counts, because one photon can reach this detector and one photon can reach this detector. Now, here's some work that we've done in my group in Ottawa. This is Ebrahim Karimi. Was a postdoc when we did this work. He's now an assistant professor in our department, physics department in Ottawa. And here's the idea. The Hong-Ou-Mandel effect is a measure of this distinguishability between two photons. So what we have done is to develop methods to control the transverse structure of individual photons. So here is a photon in which well, these are the holograms that would generate the photon. So here the inner part of the beam diffracts off of one spatial period, the outer half off of a different spatial period. So the inner half and the outer half of the transverse wave function have different orbital angular momenta content. So this photon then is distinguishable from this photon because the radial degree of the radial dependence of the field is different in this case than in this case. So we did that experiment, and we show that if the photons are completely, even though they have a complex structure, if both of them have the same complex structure, they are indistinguishable, and we get a curve that looks like this. If we make them similar but not identical transverse structures, the Hong-Ou-Mandel dip does not go all the way to zero. But if we have entirely different transverse structures for the two photons, they become entirely distinguishable, and the Hong-Ou-Mandel dip disappears entirely. Okay, so this is just an example of what we are doing and what people are doing in this field. We are learning how to manipulate the quantum statistics of individual photons. We can, at will, make them distinguishable or indistinguishable. Okay, something else that's very important in quantum information is how to develop a single photon source. Reason it's important, well, a laser beam is a coherent state. There's a statistical distribution of the number of photons in that state. And for some, it's just common sense. There are some quantum protocols where you really want to know how many photons are there. And there are other, and the most important number to know is there is one. Because if you can form a state of light, a Fock state, that has exactly one photon in it, you can do this for quantum computation, quantum communication. So it's very important to be able to generate states of light that contain exactly one photon. So how do people do it? Well, the best thing is to build a true single photon source. And the key way of doing it is that you put a single atom into the interaction region. You excite it with a laser beam. A single atom can either be in the ground state or in the excited state. If it's in the excited state, it can emit a photon, but if it's in the ground state, it cannot. So if there's only one atom in the interaction region, it can emit only one photon at a time. You choose the time window of your detector, and then you know that you have a single photon there. This is the hardest one to do. Next thing you can do is to use parametric down conversion, which ensures that the photons are created in pairs. Then the detection of one photon ensures that the other photon is present. This is called a heralded single photon source. Well, maybe it was obvious from what I said, but you put a detector here and you put a detector here. If this detector goes click, then you know that there was a photon here. So this is not a single photon source on demand. Right? Nature decides nature decides if and when that photon is going to be emitted. But at least you know after the fact that there was exactly one photon in this beam of light. And the cheapest way of doing this is to simply use a highly attenuated laser beam. Now, if you attenuate it highly enough, you're almost guaranteed that there will be at most one photon in the interaction region. Why is that even plausible that this is useful? Well, if there's no photon there, you don't detect anything. So you can call this post-selection if you want. I mean, it's inefficient on the use of your time to sit there and wait and wait and wait and wait, and finally a photon arrives. But you know that, for example, if on the average there's going to be 1/10 of a photon per time interval, and you look at the properties of the Poisson distribution, you find that it's extremely unlikely that there would be 2 photons there. So this actually works surprisingly well, except for the inefficiency that most of the time you're measuring nothing. So this is some work of Svetlana Lukishova, one of my colleagues at Rochester, and there's far too much detail here. This is after I cleaned up her visual. You should say, well, if you're going to put my whole life into one visual, I have to put everything there. But the point is that she has been working on developing various tricks for building single photon sources. Let me just give you one example. So she puts cadmium selenide nanoscale quantum dots into a cholesteric liquid crystal. What's the idea here? A cholesteric liquid crystal is a self-forming Bragg reflector. So you put an emitter inside of this helical structure. because it's a helical structure, only light of one polarization can propagate through the structure. The light in the opposite polarization cannot propagate through the structure. Because of that, even the fluorescence turns out circularly polarized. There is simply no mode for which the other-handedness can emit into. So a single quantum dot is placed inside a cholesteric liquid crystal. She excites this. There can be only one photon at a time coming out, and this photon has a deterministic state of polarization. And how does she know it works? Here's the Hong-Ou-Mandel dip. Let's go back a second. Let's go back a second. How do you even say this? If you build a single photon source and it repeatedly sends out a single photon, you can send this into a Hong-Ou-Mandel device. When the device is balanced, you will get no coincidence counts if it's a true single photon source. So this is the way that in the laboratory you determine that you have a true single photon source. Because if the photons arrive one at a time, you will never get coincidences. If you have a poor single photon source, maybe photons will arrive two at a time by mistake, and this dip does not go all the way to zero. So you can tell that in this, I was her co-author, by the way, you can tell that in this work, we had a pretty good single photon source, but we did not have a perfect single photon source because this dip did not go all the way to zero. Okay, so that was the first part of the talk, generating and characterizing quantum states of light. Now let's move on to quantum information with orbital angular momentum of light. And I guess just to put this straight, almost everything I'm going to tell you is joint work between Miles Paget and myself. I'm sure glad I got to talk before he did. Because maybe I will be saying things that he had intended on saying. Okay, so let me give the big picture here first. We believe that the transverse degree of freedom of the photon, especially as manifested in correlations between angular position and orbital angular momentum, is a key resource for quantum information science. Okay, big picture is, people usually say, light. Oh yeah, infinite plane wave. But we're saying, no, let's not be stupid. Let's utilize the transverse degree of freedom of the light field. Let's use that to encode information in the transverse degree of freedom. Well, orbital angular momentum of light is one example, and it's the example that we happen to have fallen into. So what are the orbital angular momentum states of light? Well, let me just give you some background. I stole this from Miles. It's on his website. So we all know that light can carry spin angular momentum. This is associated with its circular polarization. But light can also carry orbital angular momentum by means of a phase winding of the optical wavefront. So this would be an illustration of a plane wave. But if you can imagine a wavefront that forms a helix, this is the sort of beam of light that we are talking about. And beams of light of this form carry angular momentum, even if they are linearly polarized. It has nothing to do with the circular polarization. It's simply the phase winding of the wavefront that imparts angular momentum onto the beam. Well-known example are the Laguerre-Gauss modes. And if you look carefully at the expression for a Laguerre-Gauss mode, you will see that each one has a factor, e to the I L phi. Phi is the azimuthal coordinate, L is an integer, and we can call it the OAM quantum number. And decal calculation tells you that such a photon in vacuum carries an angular momentum of L h bar. Now, in case you choose not to believe me, I encourage you to go home tonight and derive this. This is a school, right? Okay, so let's see how one would go about convincing oneself that what I said is true. So let's start off with the Helmholtz equation, and then let's take the paraxial limit of the Helmholtz equation. What do we mean by the paraxial limit? Well, the transverse Laplacian you keep as it is, but the longitudinal part of the Laplacian you simplify by making what I called the other day the slowly varying amplitude approximation. So within quantum optics, nonlinear optics, this is what I think many speakers here have already shown this. This is the paraxial wave equation. Now, this is a Laguerre-Gauss mode. We call it Laguerre-Gauss mode because it's a Gaussian times a Laguerre polynomial. And what you can enjoy yourself doing tonight is to take this expression, introduce it into this equation, and convince yourself that this is an exact solution to this equation. Of course, Tony Siegman, who's now passed away, wrote the famous book on lasers and has an extended section on laser modes, Hermite-Gauss modes, Laguerre-Gauss modes, all of that. When he was visiting Rochester once, I said to him, I noticed that you didn't in your book ever prove that the Laguerre-Gauss modes are solutions to the paraxial wave equation. How would one go about doing it? He thought for a minute, said, oh, you plug it into Mathematica. Okay, okay. But now I've given this away. I've given away how you do the homework problem. You let Mathematica do it for you. Okay, but anyway, here is the e to the I alpha I. Okay, so now how would you create a beam carrying orbital angular momentum? Or in the context of this lecture, I want to take a single photon and take this single photon and place it into one of these Laguerre-Gauss modes. How would I do so? Well, conceptually, you go out and you buy yourself what's called a spiral phase plate. This is a glass plate in which the thickness increases as a function of the azimuthal angle. It's just plain thicker here than it is here. So if you send a plane wave into it, what comes out is something that looks like this. And what I like to say, I'm being taped, what I like to say is that the wavefronts get screwed up in going through this device. Okay, so that's conceptually how you do it. In the laboratory, you don't really want to do it this way. Well, if you wanted a fixed value of OAM, this is what you would do. But in the laboratory, you probably want to be able to control it, to change it. So what we do in the laboratory is we take a device known as a spatial light modulator. We write a computer-generated hologram onto the spatial light modulator. We diffract a single photon from this device, and the photon that's generated can come out into any one of the Laguerre-Gauss modes that we want. And here are just some examples of some Laguerre-Gauss modes that we have generated in the laboratory. This dotted circle is an aid to the eye. This tells you the aperture of the system. So all of these modes are contained within the aperture. Okay, now, well, not so long ago. In 2010, Miles and I started working very seriously on looking at the quantum aspects of light of light that possesses orbital angular momentum. And this was like the first serious paper, PRL, not Nature, the first serious paper that came out of our collaboration. So it's called angular 2-photon interference and angular 2-qubit states. But let me just talk you through this, not only because I'm very proud of this paper, but I think it was really a conceptual paper. It was almost an American Journal of Physics paper. It was a paper aimed at developing intuition about how interference works when you're dealing with orbital angular momentum of light. So conceptually, it was a very, very simple experiment. I don't think we said this to the editors when we submitted our paper, but all we did was we repeated Young's double slit experiment. But instead of being in the position transverse momentum basis, we were in the angular orbital angular momentum basis. And suddenly, things that you think you understand perfectly well, you discover maybe you didn't understand it so well. Because when we think of Young's interference, we're always thinking of the slits. But what if it's an angular slit? Okay, so let me tell you the details. Okay, so first of all, let me just tell you that there is a Fourier relation even in the angular domain. So let's say that you take a mask. You have, let's say, a Gaussian laser beam, but the beam falls on this mask, and you have this pie-shaped sector. Light can get through this only within this pie-shaped sector. Now, if light is constrained to be in only this small azimuthal region, by Fourier's theorem, it has to be comprised of a linear superposition of a very large number of orbital angular momentum states. And you can see this simply because there is a Fourier relation that, okay, you take the wave function as a function of azimuth, and you take the Fourier transform. This has to be a discrete Fourier transform now, and you find the amplitude of each of the OAM states that would be contained. Okay. So here you have one basis, here you have another basis. This wave function here in this basis is made up of a linear combination of wave functions in this basis. Also, by Fourier's theorem, it goes the other way around. A linear combination of these, well, the Fourier transform of a linear combination of these corresponds to some particular wave function in the azimuthal basis. Okay, so that was for a single slit. Now, how do you do the analog of Young's interference? So now, okay, we excite with an L equals 0 mode, or a TEM00 mode, or a Gaussian laser beam, but we now have two slits here. One slit here and one slit here. So you have many, many values of orbital angular momentum that are present in the field at this point. And now what you want to do is you want to measure the orbital angular momentum content of such a beam. So how do you do it? Well, you want to build, well, I'll call it a mode sorter. Maybe a mode projector would be the better word. Miles, we did not appreciate the subtle distinction when we back then. Okay, so you ask a question. You have an LG1 beam. How do I prove to myself that I have an LG1 beam? Answer, you make a computer-generated hologram with L equals -1. You take this photon, you diffract it off this hologram. The 0th order of diffraction, you just get through what you put in. The 1st order of diffraction, you add this quantum number to this quantum number, you get an LG0. The -1st order of diffraction, you subtract these quantum numbers, you get an LG2 beam. Now, you try to couple this output into a single mode fiber. Only the LG0 beam will couple into a single mode fiber. If you try to couple an LG1 beam into a single mode fiber, well, you succeed perfectly, but only the hole in the middle of the donut couples into the single mode fiber. So it was Anton Zeilinger who came up with this trick to determine the OAM spectrum of a beam of light. So here's how you do it for L equals 1. And, well, of course, well, if you wanted to build one for L equals 2, well, then you do the obvious thing. You take a computer-generated hologram for L equals -2, and once again, only if this is an LG2 beam will you get a photon injected into this fiber. Okay, so how did the experiment work? So we want to see what is the OAM spectrum from a double slit. Well, the OAM spectrum from this slit would have one value. The OAM spectrum from this slit would have a different value. Since these are indistinguishable processes, you add the amplitudes and then square. So you add these amplitudes, you square, and this is what you find. So so this is Young's interference fringes in this new basis set. But note that this is plotted as a function of the orbital angular momentum quantum number. So it looks like fringes, but it's in a very, very different space than the one we usually think of when we're talking about orbital angular momentum, when we're thinking about Young's interference fringes. Okay, so that was the simple part. Then we said, well, what about two-photon interference? I mean, this is actually getting quantum now. So we have our parametric down converter, and we send one photon to this slit, we send the other photon to this slit here, and we have our mode projector here, we have a different mode projector here, and we look in coincidence and say, how often does this detector click, and simultaneously does this detector click? And let's just jump to this one here. So here are our coincidence counts plotted as a function of the L. I'm not allowed to leave the penalty box. Right? Talking like a Canadian is scary, right? So here, holding, does that say L sub I? Holding L sub I equal to +2, here the coincidence counts plot as a function of L sub S, and you get these interference fringes. Now, what can you do with this result? Well, I could have an argument. I wouldn't argue with Miles, but let's just say that in concept you can imagine that I would have an argument with Miles, and I say, my photons are entangled better than your photons. He says, no, my photons are better entangled than yours. So how do you quantify the thought of how strongly two photons are entangled with one another? Well, one of them is something called the concurrence, and this was a measure that was introduced by Bill Wooters, and a simple calculation tells us that the visibility of the interference fringes here, in the limits in which this experiment was conducted, the visibility of these fringes, which we measured to be 0.93, is equal to the concurrence. So the visibility of these fringes tells us how well entangled these photons were with one another. Okay, so then we moved on in this, and we said, well, can we look at EPR type correlations in the angular OAM variables? So I had just shown you work from 10 years earlier by John Howell and myself, in which we had studied EPR correlations in position and transverse momentum. But now, since we're so intrigued by orbital angular momentum of light, let's repeat that experiment with the angle OAM variables. So, conceptually, this is how you do it. We have an ultraviolet laser, BBO nonlinear crystal, two entangled photons, different hologram in each one of these arms. We see if the light reaches our detector. It's an avalanche photodiode operating in the Geiger mode. It's a single photon detector. And we ask, is there a coincidence between a click here and a click here? So we can look both at correlations in angular momentum, well, I'll jump right ahead, or correlations in angle itself. Let's come back here, correlations in angular momenta. So, we set up, so we put a hologram onto our spatial light modulator that will project this into a given orbital OAM mode, and we look at the correlations between the OAM value of the signal photon and the OAM value of the idler photon. And we find that, well, here's what it looks like in a grayscale, and here's a plot through the center of this, and you see that you get a very, very strong correlation here. And we can call this delta L the spread of the correlation. We can repeat the same thing in the angular variables. So now we put on the spatial light modulator one of these angular slits that separates out only a given pie-shaped wedge, and we measure the probability distribution as a function of the angular separation between this slit and this slit. We measure the width of this distribution, and then I've repeated them down here, and here's just a reminder of how the experiment works. So you multiply these two uncertainties together, and you get 0.024, which is, again, 10 times smaller than the Reed EPR bound. So what does this mean exactly? It's easy to say it wrong. I won't say it wrong. I'll say it wrong. Many people who work in this field, they write their paper and say, I've gotten 10 times better than the classical limit. This is not the classical limit. It's 10 times better than the quantum limit if the particles were independent from one another. Okay, so we measured correlations that are 10 times stronger than allowed by the Heisenberg uncertainty relations for independent particles. So the EPR conclusion, well, so what's the point? It's that quantum mechanics, what was their conclusion? It's that quantum mechanics either is incomplete or non-local, holds for angle OAM type of entanglement as well as in position momentum type of entanglement. So crucial. This was their conclusion. Of course, they said it was obvious it couldn't be. EPR said it's obvious it cannot be non-local, so it must be incomplete. But I think the current understanding is more the opposite. That quantum mechanics, 100 years later, we haven't found a mistake. It's probably complete, and we just have to accept the fact that quantum mechanics is non-local. Okay, so. I just said that. Let's just go on. Oh, okay, so something else that we are doing more recently in Ottawa is to build is to work on the concept of a Q plate. A Q plate is a quantum interface. And the idea is that maybe Germany encodes in the polarization degree of freedom, but maybe France encodes in the orbital angular momentum degree of freedom. Talking about quantum information now. So when packets of quantum information flow from Germany to France, you have to have an interface that converts the quantum information from one type of encoding to another type of encoding. I'll call that a quantum interface. So there's a device that does this. It's called a Q plate, and it converts spin angular momentum into orbital angular momentum. Now, Q plates historically, well, they were invented by Lorenzo Marucci in Naples and his graduate student at that time, Ibrahim Karimi. And what a Q plate does, it's a liquid crystal structure in which there's an azimuthal symmetry is induced. It's a quarter wave plate with azimuthal symmetry. And if you think that one through, make sure you have a little bit of time before you try to think it through. If you send in left-hand polarized light, you get out right-hand polarized light. But of course, then by conservation of angular momentum, you will pick up 2 units of orbital angular momentum. Again, if you send in a Gaussian beam right-hand polarized, you get out a beam that is left-hand polarized with -2 units of orbital angular momentum. Okay, so it converts spin angular momentum into orbital angular momentum. So one of the things we did very recently in Ottawa, I mean within the past year, is to build the world's thinnest Q plate. So it's a plasmonic Q plate. So here it is. It's a glass substrate, thin layer of ITO for conductivity, and then L-shaped nano antennas fabricated on top of that. Maybe look at, here are successive magnifications of what's going on here. So we arrange these L-shaped antennas in a circular pattern. You can see the circular pattern here. This is an SEM image of what these nano antennas really look like. So, okay, so it's 30 nanometers thick. So it's plasmonics. I mean, we all love Dove prisms, right? But Dove prisms are about that thick. There's been a theme developing over the past 10 or 15 years or so that using structured surfaces, in this case using nano antennas, you can make polarizing optics that are very, very thin. In this case, only 30 nanometers thick. And here's what happens if you take the output of the nano Q plate and interfere it with a plane wave. You get this interference pattern, which should look familiar to you, because 4 slides earlier I told you that this is the pattern that we put onto our spatial light modulator if we wanted to form a beam hearing orbital angular momentum. You can use this in reverse to ensure that the beam does carry orbital angular momentum. You interfere it with a plane wave and you get a structure that looks like this. What time did I start? 10:30 I started. Okay, good. Okay, so good. I'm not going to use up my 2 hours, nor do you want me to use my 2 hours. Okay, so next subject is quantum imaging. So what in the world do we mean by quantum imaging? So quantum imaging strives to form images with better sensitivity or higher resolution through use of quantum states of light. And it also can be used to perform indirect or stealth imaging. For example, using a very, very small number of photons. Maybe you want to look, but you don't want the person to know you're looking at them. So you don't use a floodlight like they do in the detective movies. You want to illuminate the target with an extremely small number of photons and still get the best possible image that you could. So these are just 2 examples of why people are interested in quantum imaging. More broadly, by quantum imaging, we mean just doing imaging, microscopes, telescopes, but let's utilize the quantum nature of light and let's see if you can build better image-forming devices by exploiting the quantum nature of light. Now, I just love this word quantum imaging. So those of us who were watching television in 1953, we can raise our hands, or maybe we will choose not to. Remember that there was Sid Caesar and Imogen Coca, and they were the primary, one of the primary comedy teams. So whenever I hear quantum imaging, I think of quantum imaging, and I think of this whole community of people going out and studying quantum features of Sid Caesar and Imogen Coca. You know Sid Caesar, right? No, I mean he became a movie producer then. Through the 80s and 90s. Okay, that's Sid Caesar. Okay, so let me give you an example of quantum lithography. This is an idea that John Dowling came up with, and he points out that entangled photons can be used to form an interference pattern with detail finer than the Rayleigh limit. So he is serious, or at least he's sort of serious, that maybe using quantum states of light, you can do optical lithography, forming feature sizes that are much smaller than what is currently available. Now, you say, but we already know how to make very small feature sizes. And John Dowling would say, yeah, but now you can make them even smaller if you combine quantum methods with the tricks that people are using now with lithography. Okay, so let's take a look at his idea, because it's very intellectually intriguing, leaving aside how practical it is. So you have a laser beam. It excites a parametric down converter crystal. You end up with two indistinguishable photons. They meet at a beam splitter. Half the time, two photons leave in the upper port. Half the time, two photons leave in the lower port. You then allow them to interfere on some screen. The nature of the interference is not classical interference, it's quantum interference. The probability amplitude that both photons come through the upper arm interferes with the probability amplitude that both photons come through the lower arm. If you work your way through this, you find that this interference pattern is twice as dense as the classical interference pattern that you would see under these conditions. Okay, that is standard quantum technology. John Dowling, the difficult part here is he says, let's imagine that this lithographic material works by two-photon absorption, and let's assume that it is so sensitive that the extremely weak light that comes out of a parametric down converter would be enough to register a strong signal on this lithographic plate. So he proposed this in the year 2000. I would say that there is still no complete laboratory demonstration. I can say that without offending people, because one of the incomplete laboratory demonstrations was my own. And Yanhua Shi also had his own incomplete laboratory demonstration. You see the intellectual intrigue by this, although it really has never panned out, except that then you think about it, that instead of doing lithography, maybe you could use this to do microscopy. That removes the requirement that you have this extremely sensitive recording material. So, in fact, this is what, okay, so this is the idea that we pursued more recently in my own group. There's a very bright young man named Mankei Tsang, who was at Caltech at the time, and pointed out that that if you give up on trying to do lithography and just want to use this to do microscopy, there's a much easier way of doing it. You just you have a photodetector array, and you just see which pixels fire on each photon pair, and you calculate the centroid of the pixels that fire, and that will give you exactly the same information that you would have gotten out of John Dowling's method of recording this on a lithographic plate. So here's results from my group. This is the classical interference pattern, and this is the quantum interference pattern, showing a doubling of the fringes. So the follow-up work that we have not done yet, but one of these days we're going to do, is to take a test particle and scan it slowly through this region here. So I mean, here we've just cast an interference pattern. We haven't shown it could be useful, but if you can localize the position of a particle to this accuracy instead of that accuracy, that could demonstrate that this quantum metrology can actually be useful for making precise measurements. A comment I want to make, nearly ideal CCD cameras are now commercially available. I think people don't realize this, except for Miles and me, and we are on a mission to tell the rest of the world about this. So you ask yourself, what do I mean by an ideal camera? An ideal camera would have 100% quantum efficiency and a vanishing dark count rate. And the world is there, or very, very close to being there. There's two ways you can imagine doing this. there's two types of high-end cameras. One's called an intensified CCD. The other is called an electron multiplied CCD. Intensified CCDs have a quantum efficiency of only about 20%, but they can be gated. And if you know when your photon is going to arrive, you are looking at dark counts only during that brief nanosecond, 10 nanosecond window when you know the signal is going to arrive. There are essentially no dark counts during that. So this is one idea. The other is an electron multiplied CCD. This has a detection quantum efficiency of about 90%, which is better. It cannot be gated, but the background count rate is only like 0.02 counts per pixel per readout. So you say, well, that's almost zero. But then you say, well, there's probably 1,000 pixels in this. So maybe over your field of view, you have 20 spurious readings. So depending on what you want to do, maybe that is noiseless and maybe it's not. But just to test this out, this is an experiment that Miles and I did. Imaging high-dimensional spatial entanglement with the camera. Let me motivate this a little bit. This is actually what you see if you look at parametric down conversion. I think nobody at this conference said this yet. If you look at parametric down conversion, it comes out in rings because different colors of light will phase match at different emission angles. So you get a pattern that looks like this. Sasha Sergienko took that photograph. I mean, he's a good person. It's in the public domain. He put it on Wikipedia, right? I mean, it means anybody can use it. But it was Sasha who actually took that photograph in Anton Zeilinger's group. Now, most people who do quantum information do something that, well, they do it because they have to, but it's pretty silly. They put a single mode fiber here, and they put a single mode fiber here, and they look for correlations between this light and this light. We throw away 99.9% of the entangled photons that come out of the system. But if you had a camera, and the camera was sensitive enough, you can look at this entire field of view simultaneously. So that is what Miles and I and co-workers did. So you can have your camera, the EMCCD camera. It was looking at the image plane of the parametric down conversion crystal, or you could also have the camera look at the Fourier plane of the parametric down conversion crystal. And this shows the incredibly high quality of the correlations. Here in the near field, well, this is the pixel for one of the photons. This is the position pixel for one photon, position pixel for the other photon. Here's the momentum pixel for one photon, momentum pixel for the other photon. Note the extremely high correlation. So now we calculate that we were looking simultaneously at 2,500 spatial modes. And since we had a lot of data here, we can once again take a look at the Reed EPR criterion. And this is even smaller than the numbers I was mentioning before. Maybe I should go into a little more detail about what the notation means. Not just to explain what I'm talking about, but also because it's very important to understand how many of these measurements work in quantum information science. This means the uncertainty in X1 given that you know the position of X2. This means the uncertainty in the momentum of particle 1 given that you know the momentum of particle 2. We call these conditional uncertainties. So in quantum information, this is often what we have. You have two entangled particles. You want to know what is the distribution of this particle given that you've made a measurement on the other particle. Okay, this is cute. I'm not sure it's useful, but it's cute. Something I've worked on. It's called quantum secured surveillance. how do we know that what we're looking at is real? Think in a military context. Maybe we just want to look and see at aircraft that are flying up overhead. And how do you know that the aircraft really is what you think it is? Maybe the devious person on that airplane has stolen your photons and replaced them with photons that make it look as if it's just a bird flying overhead. So how would you do that? Well, I'll talk about this later. In standard quantum cryptography, Alice wants to send something to Bob, and there's a possibility of an eavesdropper somewhere in between. This is a related but somewhat different protocol. Alice and Bob are now in the same bunker, let's say, but here's the object under surveillance. We'll call it Jim the jammer, who's trying to jam their signal. And the question is, how would Alice, how would you do the surveillance in a way that you know that somebody has not been spoofing you by sending a spurious signal back to you? So it's a procedure very much akin to the intercept resend attack in quantum cryptography. Okay, so let's say that it's some stealth aircraft here, but that they're trying to spoof you by making you think that you're looking like a big bird. So a little bit implausible, but okay, so they're stealing your photons and replacing them with photons that have a different transverse structure. So here's what we do for each time we send out single photons, and we randomly change the polarization of the photon from being vertical, horizontal, diagonal, or anti-diagonal. And then over here, we also look and we make sure that the polarization that we receive is the same as the one that we sent. If the spoofer or the jammer were intercepting our signal, the spoofer could never know with complete certainty what polarization we were having. The person would send back a photon with Jim's best guess as to what the polarization was, but half the time Jim would guess wrong. So there'd be spurious, so the return signal would end up in the wrong polarization channel here. And in fact, if the error rate is less than 25%, you know that the protocol is secure. You cannot prevent the person from spoofing you. So you might get back an image that looks like this, but you would have an error rate that is more than 25%, and you would thus know about it. Now, pretty silly idea, except that the semi-popular press picked up on it. I guess MIT is sometimes taken too seriously. But I went to MIT, by the way. So MIT picked up on this, put it on their website, and then everyone else picked up on it and put it on their website. And then something called Business Insider says that new imaging system could make America's stealth technology obsolete. It says, this won't be good news for Lockheed Martin, that my students and I are going to put them out of business, but by showing that the new F-35 fighter will not perform as claimed. This too complicated to explain. Too complicated to explain. We'll leave that one for Miles. There was also joint work. Okay, let me come at the same thing, but from a slightly different point of view. How much information can one photon carry? So if you think wrong, you say a photon is either there or it's not there. So a photon can carry one bit of information. And there are people who thought that, well, maybe they still do today, but both Miles and I were part of a DARPA program in the US that was aimed at trying to quantify exactly that question of how much information can you carry on a single photon. And now we're coming back to this transverse degree of freedom. If you exploit the transverse degree of freedom of an optical field, you can carry a lot more information on that field. Let me give you a almost trivial example of this. Consider a photodetector array, and I will send a single photon, and I'll aim the single photon so that it hits, so it's aimed to hit different elements on this array. So, I mean, here's a demonstration that a single photon can carry massive amounts of information. You just aim the photon to hit different spots here. Okay, so this is a demonstration that a single photon can carry lots of information, but maybe not in the best possible way. So one of the very first things we did when we started asking how much information can be carried by a single photon was to impress an entire image onto a single photon and later recover the image. John Howell and I did this together. I said, John, this would be a 50-50 collaboration. I will impress the image on the photon and you have to get it off. Okay, so our procedure was to sort the photons into classes determined by a predetermined set of images, and we used holographic matched filtering to do the sorting. And we used heralded single photons created by parametric down conversion. So here's how we built the matched filter. We have some object. We illuminate the object by a beam of light. We interfere this with a reference plane wave. We record this on a holographic plate. We take the same holographic plate, replace object A by object B, and interfere this with a reference plane wave, but coming in from a different direction. This is then is called a multiplexed hologram. There are two holograms on the same substrate. Now, how does the readout work? You take a single photon. Here's the object. You don't know whether it's object A or B. The single photon passes through it. You have an unknown image. The image falls onto the hologram. But if the object were object B, this photon leaves in this direction. If it was A, the photon leaves in that direction. Well, I'll say the technique scales to more than two images, because you can have more than two directions for the plane wave. So we did it. And the artificial question is, can we distinguish UR from IO? So we record a multiplexed hologram with a UR and an IO onto it. And this shows the readout. So if you send a UR into this, well, this is the direct transmitted beam. So don't look at that. If you send the UR into the hologram, you get a beam that's diffracted off in this direction. If you send an IO into the hologram, the first order diffraction ends up here. So we did this demonstration with intense light, so I have a pretty picture to show you. But then when we actually did the experiment, we put a avalanche photodiode here and an avalanche photodiode here, and did the experiment with heralded single photons. And okay, so here the count rate in the wrong channel is very, very much smaller than the count rate in the correct channel for either the UR or the IO type of object. So this shows that that we can distinguish two objects even when they are only illuminated by a single photon. So, yeah, so it's just working our way up to this, to doing useful things, even though you only have a single photon at a time in the interaction region. Now, another thing I have to tell you about is something called ghost imaging or coincidence imaging. This was invented by Yanhua Shi in Maryland and David Klitschko from Moscow. Boy, all my slides start the same way, don't they? You see, in quantum information, there's a few number of tricks we have, and we try to play these tricks over and over again. Okay, so laser beam excites parametric down conversion. You have two entangled photons. One of these illuminates an object. If this photon gets absorbed, this detector does not go click. If the photon does not get absorbed, the detector does go click. You take the other photon, you send it to a photodetector array, and you look in coincidence. And it's called ghost imaging because you get an image formed here. You get an image here of an object there, and the photons actually form the image, have never physically interacted with the object. It's pretty obvious how it works, but it sounds very, very strange until you think it through, in which case it becomes obvious. But this has obvious applications to remote sensing, to color. I mean, whoever says that these photons have to be at the same wavelength. There was a debate at one time whether this is a quantum mechanical process. The answer is no. You can do this with thermal correlations just as well. Okay, so this is ghost imaging. So then in the context of this, how much information can be carried by a single photon, we said, well, can we do single photon coincidence imaging? So here was the idea. We have four objects, A, B, C, or D, and I can put any one of these objects here. I have a source of entangled photons, and I have a multiplexed hologram, but in this case, there were four different holograms multiplexed under the same substrate. So BBO crystal generates entangled photons. One of these photons goes to the right. If the detector goes click, it means that the photon has passed through this mask, and it means that the photon has acquired the transverse structure of this mask. Since it's entangled to the other photon, it means that this photon also has acquired this transverse structure, and hence it will diffract into this direction. So it's a purely quantum mechanical effect. Here we've measured the coincidence count rate when the object is either A, B, C, or D, and the detector is either A, B, C, or D. And you see you get very strong peaks on the diagonal and very weak peaks in other directions. So only a single photon illuminates the object, but we can reliably distinguish among these four different possibilities. Okay, use of quantum states of light for secure communication. I think there are other quantum cryptography talks at the workshop. Yeah. Okay, so I will very quickly talk about secure communication, just as an introduction, and tell you what we've been doing on this project. So this will be a tutorial introduction to the talk later on in the workshop. So use of quantum states of light for secure optical communication. Okay, well, there's something called the BB84 protocol, which we'll hear about more this week. But this was the original protocol of Charlie Bennett and Gilles Brossard in 1984. That's why it's called BB84. They had a procedure for absolutely secure communication. It's based on the properties of quantum mechanics, based on the thought that in one measurement you can never measure the complete quantum state of a quantum mechanical particle. In their case, they were encoding in the polarization degree of freedom. It meant that each photon could carry only one bit of information. We have built a QKD system that can carry more than one bit of information per photon. And our procedure is to encode using beams that carry orbital angular momentum, such as the Laguerre-Gauss states. I didn't say this before, but the Laguerre polynomials, well, we're in France, they form an infinite set. So mind-boggling. Right? If I can reliably take a single photon and put it into any Laguerre-Gauss mode, there is in concept no limit to how much information can be imposed on that photon. And just to to get your attention, in traditional telecom, we use many photons to carry 1 bit. We have demonstrated with Miles a quantum protocol in which we can carry more than 1 bit per photon. We've just taken the world and turned it topsy-turvy. Of course, their bit error rate is a lot smaller than ours, but let's not. But let's talk concept at least for now. Okay, so we're developing a free space QKD system that can carry many bits per photon. We encode either in the Laguerre-Gauss modes or in their linear superposition. So here are the first 27 Laguerre-Gauss modes, going from L equals -13, -12, -11, -1, 0, 1. 27, that's about the number of letters in most alphabets. So we're saying that this is a human type of encoding. You can really carry, you don't have to use ASCII or something like that. You can really transmit any letter of the alphabet. One of the features of the BB84 protocol is that you need the ability to transmit in either of 2 bases. So one of our bases is the Laguerre-Gauss basis itself. The other basis is a equally weighted superposition of each one of these. So you take an equally weighted superposition of these with varying relative phase, you can get any one of these. So this is one basis. We call it the Laguerre-Gauss basis. This is the angular basis, and it's called the angular basis for the obvious reason that by construction, these consist of lobes sticking out in different directions. These 2 bases are said to be mutually unbiased, which is also crucial for the protocol and other protocols in quantum information to work. What we mean by mutually unbiased is that if you take the projection of this mode onto one of these, say this one here, you get exactly the same as the projection of this onto that, or of this onto that. And you can see that just by inspection, that these are azimuthally symmetric. These are identical, except they are sticking out in different directions. So this basis set and this basis set are mutually unbiased. Okay, so how does the experiment work? Well, in the actual experiment that we've just done, just published within the past month in New Journal of Physics, we didn't do the whole 27. We only used 7 states. Well, you need an avalanche photodiode for each channel. And even with DARPA money, we couldn't afford 27 avalanche photodiodes, which go for like $5,000 to $10,000 each. Okay, so I think you don't want to know all the technical details. So we have a highly attenuated laser beam. I said you can fake a single photon source, but by a highly attenuated laser beam. So I said that's the poor man's way of doing it. Okay, we did it that way. Highly attenuated laser beam, an acousto-optic modulator carves pulses out of this laser beam. Well, a digital micromirror device is a functional equivalent to a spatial light modulator. We impress any one of these modes onto the beam. This is Alice, this is Bob. Traditionally, Alice is trying to transmit to Bob. So this is the communication channel here. Now, Bob receives one of these modes, and well, he chooses at random whether to measure in this basis or in this basis, but whichever one he chooses to measure in, he has the daunting task of trying, he only has one photon, he can only make one measurement, so how in the world does he know which one of these he has? If it was classical light, you do interference and you just look at what the wavefront structure is. But if you only have one photon, you can't do interferometry, so you have to figure out a way of doing this. And I had spent more years of my life than I'd want to admit trying to build holograms that could do this sorting process, and it was never very successful. Then Miles came up with a very clever way of doing it, which is illustrated here. He builds something that is called a sorter, and the sorter, the key element here is a very, very funny lens. Very, very funny lens. It's a lens made so that if the object is a donut, the image is a hot dog. So maybe look at my arms. I can't walk across it. So as the beam propagates, there's a branch cut and unfolds and turns into a straight line. Now, and as the azimuthal distribution around a donut, it's very hard to measure. But a linear phase ramp along something like this, a plane wave, is called wavefront tilt. So suddenly an extremely difficult problem turns into a very simple one. So you just put a lens there, and depending upon where this beam of light hits, that tells you directly what the orbital angular momentum value is. Slight variation on the theme for the angular basis, but time is fleeting. Okay, so these were the laboratory results that we got. I know this looks very boring, but if the whole idea was to transmit a strings of ones and zeros, and I want to convince you that we did it, I have to show you a string of ones and zeros. So here's the strings of ones and zeros that we transmitted. But then I wanted something to look a little more impressive. And there was this Persian guy named Xerxes. So this is called the Tablet of Xerxes. And the lead author on this paper is Iranian. So he took a photograph of the Tablet of Xerxes and digitized it and then encoded it using this shared string shared by Alice and Bob, transmits it. Now, if somebody enters, there's no attempt made to keep this secret because it's encoded with a secret key. So this is sent over a public channel. Anybody seeing the signal just sees, you don't call it white noise, colored noise. But then when you do the decryption at the very end, you end up with the same image that you had sent. There's a whole research area known as security of quantum key distribution. And well, ours is, so we've applied the standard tests, and the tests tell us that our procedure is secure. Oh, and the very next step is that we, well, in this, what? There. Okay. In the earlier work, we were transmitting maybe 10 bits per second. Not enough to get people's attention. We are right now with Alan Wilner building a new system that will encode at gigabits per second. And we think there might be some real impact there. I'm going to try to wrap up. I was going to talk about some related work. I'll just tell you the fun parts of the related work. I've been at this an hour and a half. Okay, so this is our new building in Ottawa. So the University of Ottawa has embraced photonics. I mean, it just makes your heart go pitter-patter to know that you're at a university that cares about what you care about. This is the $65 million new research labs that the University of Ottawa has just built for Paul and me. Well, a few other people as well, but this is the building they built for Paul and me. And here's some of my things that I'm working on. Okay, so when I came, I was told that I could hire 3 other people to work with me, and 3 assistant professors, and they are now named as Ksenia Dogoliva, Jeff Lundin, Ibrahim Karimi, and through very good luck, we were able to get Gerd Loix to come and be an adjunct professor in our department as well. I'm not going to go through the details. This is something we're also very proud about, just published in Science within the past several months. You've all heard about Möbius strips, and probably as children, We all built Möbius strips as children. But when you think about it, how often have you gone outside and seen a Möbius strip occurring spontaneously in nature? It's very, very unusual. They, as pervasive as they are in junior high school, they are not pervasive in nature. What we've found is that if you form a structured light beam and form it in exactly the right way, the polarization forms a Möbius structure. So here is the axis of the light beam. You go around this, you plot the direction of the polarization for every point along this ring, and you find that when you get back to your starting point, the polarization has flipped top to bottom. So the polarization of light actually forms a Möbius structure. That's cute, right? That's something you can stand up in public and tell people about. But then they say, why is this important? Maybe it isn't. It's the technology that's important. I didn't say this. You get Möbius structures only if you focus if you focus with a numerical aperture of 1. It's the Z component it's the presence of a strong Z component of the field that allows you to measure a Möbius structure to begin with. So we, especially Gerd Loix, has developed methods for measuring all 3 field components, amplitude and phase, of an electromagnetic field at with 10 nanometers of resolution. So it was the technology that allowed us to do this, which I think is probably just as important as the thing itself. Oh, this is so cute. I bet that BP wished that they hadn't used this as a commercial 10 years ago. You get the joke, right? No, it's clear I've been talking too long when nobody knows why this is supposed to be a joke. Okay, the last one, and there really isn't time to talk about this, is we've shown how we can increase Fresnel drag by a very large amount by making use of slow light materials. Key author here is Akbar Safari. And one of you said you even was an undergraduate student with Akbar? Somebody here. Somebody who, you're going to say somebody who clearly didn't bother coming to the lecture. No, but you're here. Okay, so let me just skip to the end of this, because there's another point I want to make. His name is Akbar Safari, and I just want to please take very careful note of the correct spelling of his name, because you would never want to confuse it with Admiral Akbar. Now, I think in a community like this, we are all Star Wars fans, right? So we all feel that Admiral Akbar is almost a member of our family. But please note that just one letter of the alphabet can make a huge difference. So to make it clear, this is my graduate student, this isn't. And while we're on that subject, there are other humorous situations of sound-alike names, because the Cardassians and Kardashian, they're spelled differently, they're pronounced the same, but they are very, very different entities. Okay, so this is going to be the last slide. I just want to tell you that I'm not the only person who appreciates round eyeglasses, and we'll see how many of these people you can identify. So thank you very much.